You know that simple beep from a hearing test? What if I told you it's one of the most powerful diagnostic tools in all of medicine? Seriously, it's not just some random sound, it's a precision instrument crafted from pure physics that can uncover everything from subtle hearing damage to much more serious issues. Today, we are going to pull back the curtain, deconstruct that beep, and show you the incredible science that makes it all work.
We've all seen this chart, right? This is the roadmap of a person's hearing. It shows us with incredible detail the quietest sounds they can hear across the whole range of pitches. It's our gold standard for a reason. And how do we build this amazingly detailed map? With nothing more than those simple beeps, or to be more accurate, what we call pure tones. We play them at different pitches and volumes to find the absolute edge of a person's hearing ability.
But why a beep? I mean, why not a word or a snippet of music? How can a sound that is so basic be precise enough to diagnose something as complicated as hearing loss? Well, the answer is hiding in the beautiful, invisible dance of sound itself. So, to really get the power of that beep, we have to start at the very beginning. We need to look at what a sound wave actually is, right down to the level of individual molecules. At its core, a wave is really just energy on the move. And for sound, that energy travels through the air. Now, the best way to picture this isn't as an object flying across the room. Think of it more like a domino effect, a chain reaction where energy gets passed from one air molecule to the next, to the next, to the next. Okay, so how does this chain reaction even get started? To make this invisible process really easy to see in your mind's eye, let's use a classic example that every student of acoustics learns, the tuning fork. So when you strike a tuning fork, its little arms, or prongs, vibrate back and forth like crazy. As a prong swings outward, it pushes the air molecules right next to it all together. And then, as it swings back inward, it leaves a little gap, pulling those molecules apart. It's just this constant rhythmic push and pull. And, of course, we have scientific terms for these actions. That push, where molecules get packed together and the pressure goes up, that's called compression. And the pull, where they spread out and the pressure drops, is called rarefaction. So compression, rarefaction, push, pull. Simple as that. Now, here is a super important point that trips a lot of people up. Those air molecules, they aren't actually flying across the room and into your ear. Nope, they're just kind of wiggling in place, passing the energy along. So, what does that wave of energy actually look like? Sound is what we call a longitudinal wave. The particles themselves move forward and back in the same direction the energy is traveling. This is totally different from, say, a ripple in a pond. That's a transverse wave, where the water moves up and down, which is perpendicular to the way the wave is moving. And that right there brings us to the million-dollar question. If sound is this forward and back, longitudinal thing, why does every single textbook, every piece of software we use, show it as an up and down ripple-like wave? And the reason is actually really simple. It's a map. It's a graph. We aren't drawing the physical movement of the air. We're graphing the change in pressure over time. And that visual chart of the pressure peaks and valleys makes the wave so much easier to measure and analyze. That very specific, smooth, repeating shape that we graph has a special name, and it is the absolute key to understanding the pure tone from our audiogram. It's called a sine wave. A sine wave is the graphical fingerprint of the purest sound possible. It's this perfect, smooth oscillation that represents just a single frequency of vibration, with no other tones or harmonics mixed in to muddy the waters. So when we look at this graph, that highest point of the wave, the peak, that lines up perfectly with the moment of maximum compression, when the air molecules are squeezed tightest and the pressure is at its absolute highest. And you guessed it, the lowest point of the wave, the trough, represents the moment of maximum rarefaction. That's when the molecules are spread the furthest apart and the pressure is at its absolute lowest. So what about that line running right through the middle? Well, that's just normal, resting air pressure. It's the state of calm before the sound wave came along and shook things up for a moment. Okay, let's pull all this physics back into the real world, back into the clinic, and connect it to what we do every day. Why does any of this actually matter? Here's the most important part. Because a pure tone is a perfect sine wave with only one frequency, we can isolate and test a person's hearing at that one specific frequency with surgical precision. This is how we can spot the difference between general hearing loss and, say, a very specific notch at 4,000 hertz that was caused by noise exposure. There's no other noise to confuse the results. It's clean.
And there you have it. That's the secret. We've deconstructed the beep. Every single mark you place on an audiogram represents a patient's ability to hear one specific, perfect sine wave. From a tuning fork's simple push and pull, all the way to a dot on a chart. It is the foundation of everything we do.
You know, understanding this one fundamental building block opens up a whole universe of new questions. But maybe the most important one is how this perfect, clean, laboratory sound relates to the messy, complicated world of sound we actually live in every day. And that right there is the final crucial takeaway. The very reason a pure tone is our perfect tool for diagnosis is because it's so incredibly rare in nature. The real world is a chaotic, complex soup of countless sine waves all hitting our ears at once. And the science behind how our brain makes sense of that, well, that's a story for another time.